All right, those of you joining us over recording, welcome to Ops Lecture 10.
All right, really quick, previously on Ops. So this is going to be our 10th lecture. Very exciting. We have 10 available for all of you. And then last week we announced the distance sensor project. So you guys still got to get checked off for that. That's going to be your last project of the quarter. So good luck on getting that done. Today we are going to be covering 3 topics: button debouncing, pull up and pull down resistors, and finally PID control.
Yes, sir.
A few announcements. So as sure a lot of you guys know, there's a lot of broken emitters out there. We apologize for that. We have extended the deadline for the project to this Friday. So be sure to get that done. Let us know kind of ahead of time if you guys are stuck on anything. We're going to be kind of lenient on this one because, you know, the broken emitter thing. So basically you can use a light or your hand. Any way you can make the LED change color, that is good enough for us. Our lab hours are listed below, but you can also go to any officer's lab hours, get help from them, or get checked off. They have the necessary information to help you guys. Some other news is we're going to have an officer info session this Thursday at 7:30 for any of you guys interested in becoming officers. We'll talk a little bit more about that at the end.
All right, so first up is pull up and pull down resistors. And before I do that, let me actually end the poll. There we go. The poll has ended. Right? Okay, so the first question is, we're going to start off with a question. What will we read if we have this kind of setup? So I'm going to launch, I'm actually not going to launch the poll because I think my poll is broken, but type in the chat, what will digital read 2 read if we have this setup? So the thing up here is a switch, and we have 5B over here, and then we're basically reading. So what will digital read 2 output? Okay, has anyone had time to think? And also, what will analog read on 5 output? All right. So what actually happens is digital read. So this is a plot of digital read on 2, and this is a plot on analog read on pin 5. And you can see they don't really settle on one value. Instead, it's like digital read fluctuates between 0 and 1. Yeah, bro, exactly. And then analog read fluctuates between these values range. And that's because over here, when the switch is not pressed, basically, we have the pin connected to nothing. And what that does is it'll read floating values. Basically, the pin reading will be affected by the environment and like what other things are in the environment instead of the actual values you might want to read in your circuit. So instead of doing that, you might have noticed this diagram kind of looks awkward. So don't do this. What you have to do is you have to add a resistor to make sure when the switch is not pressed, you'll be reading 0. So this is what pull up and pull down resistors are all about. So basically, as we've seen before with these WAC plats, they read seemingly random values when they're connected to nothing. So we need to use a resistor to set the kind of the default value for either a button or a switch that you're using in your circuit. So if we use a pull up resistor, it'll pull up the value to high when the switch is not pressed. And you can kind of see why that is because when the switch is not pressed, this over here is an open circuit, so it'll just register the high value. And when we use a pull down resistor, it's the same concept, but instead of reading high, we'll read low. Pretty straightforward. We got some resistors on the side. All right. So choosing the right value for for your pull-up down resistor is kind of important because we want it to be strong enough to not draw too much current from your actual circuit, but we need it to be weak enough for your pin to read high when it's switched off. Because over here we have a pull-up resistor and your microcontroller, so that'll be your Arduino. So turns out the Arduino pins, input pins, have like they have high impedance. I think it's like 1 mega ohm or something. So we need pull-up resistor value to be high, but if it's too high, it'll basically create a voltage divider and we won't be able to read high value anymore. So a good number for your pull-up, pull-down resistor is like 10K ohms, or alternatively, you can choose to use built-in pull-up resistor that Arduino pins have by specifying in your pin mode, pin number, and input underscore pull-up. You might have noticed in your previous projects, doing pin mode is actually not necessary. Your code will still work if you forget to do pin mode. But if you do choose to use an internal pull-up resistor, you do have to specify in your pin mode to use that. Okay.
Any questions about any of that before we go on to the next topic? No? All right. Okay, so next we're going to talk about button debouncing, which is another issue that might happen in some of your circuits. Okay, so what exactly is button debouncing, or what is the problem we're trying to solve with button debouncing? So really quick, if you look at the bottom, you'll see a sort of mechanical diagram for these buttons, and they're made using springs. So sure as you guys can imagine, when you press the spring and then you release it, it's not going to go perfectly back to its original starting position. It'll sort of oscillate and then relax eventually to its sort of relaxed position. So what that means for a circuit is when we press it on and then let go of it, it's going to register multiple pushes, right? So if you look at these diagrams on the right, you can see that it's going up and down really fast. And that's sort of registering multiple button presses, right? Some of you guys might have noticed this on, for example, the piano project. If you press it and let go, it can still kind of have like a squealing noise. That could be from it registering multiple pushes. So what we have to do is debounce this button. So debouncing is essentially smoothing out the button press. So we want one press of our hand to equal one actual press the circuit registers. There's two main ways to do it. We could use software debouncing or hardware debouncing. So first, let's talk about hardware debouncing. And to do that, we will use a capacitor. So yeah, essentially, when we press the button and it registers and multiple presses are being registered, it's changing the voltage really fast. The capacitor can help sort of stop this because capacitors resist changing voltages. Why is that? It's because of some of the things we talked about. Capacitors take a while to charge and discharge. So if the voltage is changing really fast and the capacitor is charging up or discharging, it's not really going to be affected by it. Here is a simpler model of it. Okay, so what's going on here, right? We have R2. That is our pull-up resistor. Then we have our button S2, and then our capacitor for debouncing. So before we press the button, C1 gets fully charged, right? And the input value will read high because no current's flowing through. The bottom is like an open part, but then we press the button. So then what happens? Well, when we press the button, the input pin will read ground because it creates a short circuit there. And then we take our finger off and the spring keeps pressing the button a couple of times. But what happens during that time is C1 is charging up slowly, right? So your input pin isn't registering the multiple presses. It's going up slowly because of the C1 pin charging. And what that does is it gives us sort of like this buffer time where it gives us time for the spring to relax and go back to its normal state. And then C1 gets fully charged and then we're back at the beginning. Okay, but let's say you didn't have any capacitors handy and you still wanted to debounce your circuit. Well, you can do it using software. Essentially, we're going to do the same idea of giving us like a time window where we can't change the value. So what that does is, if we look at the pseudocode, essentially what we're doing is we're checking to see if the button state has changed. So is it high or is it low? So we're checking. And then what we do is when it does change, we're going to start a countdown or a timer. And during that time, we're going to say, okay, you can't change the value, right? Then after that time has ended, we'll reset it and say, okay, now check to see when it changes. And this effectively mimics the capacitor charging up or discharging during that time where the button is relaxing to its state. Let's see this question. If you use the capacitor, do you need to press the switch for longer so the capacitor can discharge slightly? No, you can just press it once, and then what's going to happen is it creates that short, and it's going to read the same high, and it's going to discharge really quick. And then as soon as you release the button, it'll start charging. So you don't need to hold it longer. Just pressing it the normal amount should be fine. In fact, usually when you press the button, it's like it's like many loop iterations, even if you like just hold it for a second, because the software is going so fast. You can't really act fast enough for it to have an effect.
Yep. So the idea behind all of this is that humans are slow. So whatever we do, we're gonna end up pushing the button for longer than just like one like cycle of your software, like processor. So we're going to count for that by having a debounce timer that is more closer to human movements. So maybe it'll be like 50 milliseconds or something like that. Any questions on debouncing buttons? All right. So now we're going to quickly talk about PID control. If you have taken E3, you probably heard Dr. Briggs talk about it. If you're going to take E3, you will hear Dr. Briggs talk about it. But here's our version of PID control, and with animation contributed to us by Tyler Price, who's the MicroMouse lead. Okay, so why do we need PID control, right? Why can't we just have sensor readings and like adjust constantly? Why even like have more than one term? That seems overly complicated. So first of all, we need some kind of control system for your control system, because for example, if you have a car and you want it to go straight, just because motors aren't perfect, and even if we give them the same duty cycle for the speed, it'll veer off your straight line course after a certain amount of time because they're going to run at different speeds, right? And so we need a way to constantly check and adjust for that error. And often just a proportional value. So just like reading your sensor input, like, and calculating, oh, I'm to the left of my target, so I'm going to go right. Or, oh, I'm to the right of my target, so I'm going to go left, is not enough to have a stable enough system. So what we do is instead of one, we have up to 3 parts of a feedback loop. So basically, it's a loop where we read sensor inputs and make adjustments accordingly in order to achieve some kind of target or goal. And the goal is to make the error 0 as quickly as possible, obviously. And so what we do is we tweak the constants for the proportional, integral, and derivative values to reduce the error. So now Ryder's going to talk about each of the components.
All right, yes. Okay, so first we're going to talk about proportional. So right now, I want you to just focus your attention on the blue square that's moving back and forth. What the proportional does is take the amount of error you have and sort of corrects it based on that. So if we're to the left of the line, we want to go to the right, and if we're to the right, we go to the left. What happens though is that because if we only implemented a proportional control, when it's on the left, it's going to want to keep going to the right, and it's going to overshoot the line, and then we're back on the right. On the left, same thing's going to happen. So we're going to constantly overshoot the target and just oscillate between where we should be. So in order to account for that, we have to do derivative control. So the derivative control, the derivative being the rate of change of the error, right? So it monitors sort of the rate of error. As we get closer to the line, the derivative of the error is going to go down, and that sort of creates this damping effect. You could see now with the pink, red, and yellow, that sort of mimics the change of the derivative control. So the pink, it's not quite high enough, and it still has that oscillation, which we want to avoid. Looking at the yellow, it's overdamped. So what happens there is that it's too high and it's going, very slow approaching to it. There's a nice middle ground, and it happens when it's critically damped, where it sort of doesn't have any oscillations, and it's the fastest time we can get it to settle on the line. So we want to try and get to critical damped with the derivative control. And then lastly, the integral control. For the capstone we're going to do this year, it's not super important, but what it does is it monitors the total error over time. So like an integral is like kind of like the area under the curve. This monitors the total error you've accumulated. And in this case, what it does is it helps the green square stay on the line because it's keeping the accumulated error very low. It doesn't want to add any accumulated error onto it, so it's staying on the line. That makes sense?
Yeah, so depending on your application, you'll either have PI control, PD control, or PID control. So yeah, the approach you want to take with PID control is you want to start tweaking one of the values and then see where that gets, try to get it to as close as possible. And then you start tweaking the other value and hopefully you'll reach a reasonable point where it'll be close to critically damped. Any questions or on anything we've covered so far? So far we've covered button debouncing, pull up, pull down resistors, and brief overview of PID control. Okay, if not, we have very important business to go over here, and that is next year's officer board. Whoa! Okay, so we are going to have on Thursday, March 4th at 11:30 p.m. an officer info session. And so basically, if you're interested in running for IEEE officer board for next year, you must come to this officer info session. It's not a must, but you should really, yeah. And then after the info session, at the info session, all the officers, you are going to talk about their officer positions, their responsibilities, what takes to become an officer in that position, and why you should become an officer for IEEE. And we're going to have a speed dating social Q&A kind of situation right after the info session, where you'll be able to talk to all the officers. So if you're interested, or if you just want to talk to the officers, because you might be interested, you should definitely come to this event. It's going to be on Thursday, the 4th of March. All right. And if you are interested in becoming an ops lead, you should first of all come to the officer info session, and then also feel free to reach out to us. And that's it for today's content. We have covered 10 lectures over fall and winter, and here are all the links. So if you feel like you missed ops over the break or something, or if you want to review for your possibly ops lead interview, here are the links. If you are interested in becoming an ops lead, we'll also be sending out all the links to the lectures with outlines and everything probably next week, because we're not going to have a lecture next week. So this is the last lecture of this quarter. Thank you for tuning in. It's been a great pleasure to spend 2 quarters with you guys. Thanks, Brian Wong, for reading Ops Lecture 5 link. All right now, I'm going to stop the recording.